Let me show you something strange. Imagine two curves. One sits inside the other. Any two smooth convex curves, a big one, a little one. Pick a point on the outer curve, anywhere you like. Now draw a line from that point that just barely touches the inner curve. Not through it, not across it, just kissing the surface on one side. A tangent line. That line, extended, eventually runs into the outer curve again somewhere else. From there, do it again. Draw another tangent to the inner curve, and another, and another. You're tracing out a little closed shape, chord by chord, jumping across the gap between the two curves. Here's the question: does the path come back? After some number of steps, do you land exactly where you started, closing up into a polygon? Sometimes yes, sometimes no. If you get lucky with the sizes and positions of the two curves, after 3 steps you've made a triangle, or after 4, a quadrilateral, or 5, a pentagon, or any number you like, if the geometry is just right. And if you don't get lucky, the path keeps going forever, trailing around inside the outer curve without ever closing up. Fine, that's not particularly surprising. You change the geometry, you change the answer. That's how most things work. Here's the part that is surprising. Slide the starting point. Just pick a different spot on the outer curve and do the whole construction from there. You'd expect a different polygon. Different sides, different angles, different corners, and you get one. The polygon changes completely. But whether it closes, whether the path comes home, that doesn't change. If it closed at step 3 from the first starting point, it closes at step 3 from every starting point. If it didn't close from the first starting point, it doesn't close from any starting point. Think about how strange that is for a second. The polygons you get from different starting points look nothing like each other. One is tall and narrow, one is short and wide. They share no sides, no angles, no corners. But they all agree on the exact same question: close or don't close. And they agree in lockstep. There's no closes most of the time in this construction. It's all or it's nothing. That's Poncelet's closure theorem, one of the deepest and strangest facts in classical geometry. And by the end of this video, you'll see why it has to be true, and why the reason involves an object most people think has nothing to do with polygons at all: an elliptic curve. Let me actually show you the miracle. 2 circles arranged in a very particular way. Outer circle, inner circle, offset from each other. We're going to play the game. Start somewhere on the outer circle, draw a tangent to the inner one, follow it to the next intersection. Tangent again. Next intersection, tangent again. After 3 steps we close. It's a triangle. Now just watch the starting point. I'm going to slide it slowly around the outer circle, and you're going to watch the triangle follow along. The triangle is a completely different shape at every moment. The corners are in different places, the sides have different lengths, and the third chord always lands exactly on the starting point. Always. It never misses, it never overshoots. Every starting position gives you a perfect closed triangle. Now let me change just one thing. I'll make the inner circle a hair bigger. Now watch. Slide the starting point around, and the triangle doesn't close anymore. The third chord overshoots. The polygon is open, and it doesn't matter where you start. It misses every single time. That's the all or nothing. For the first configuration, every triangle closes. For the second configuration, no triangle closes. There's nothing in between, and the boundary is razor thin. One configuration works, a configuration just a hair away doesn't, and you can't find anything that half works. Why? To answer that, we need to talk carefully about what the construction actually is, and then we need to find a hidden object that forces the all or nothing to happen. Let's set this up properly. Take any 2 conic sections in the plane. A conic is just one of the shapes you get by slicing a cone: an ellipse, a circle, a parabola, or a hyperbola. For this video, we'll focus on the nice case where the inner one sits fully inside the outer one. Call the outer conic C, call the inner conic D. Pick any point on C, we'll call it P0. From P0, there are exactly 2 lines you can draw to D that just touch D at a single point, 2 tangent lines. Each of those tangent lines, once you extend it, crosses the outer conic C at a second point. Pick one of those crossings. It's our new point, P1. Now do the same thing from P1. Draw a tangent to D, not the one you just used, the other one, and follow it to where it hits C. That's P2. From P2, another tangent, P3, P4, and so on. You're walking around the outer conic, bouncing off tangents to the inner one. The polygon closes at step N when the walk lands back on P0. 3 steps, triangle. 4 steps, quadrilateral. 5 steps, pentagon. And so on. Poncelet's theorem says this: whether the walk closes at step N is a property of the 2 conics alone. It has nothing to do with where you started. Either every point on C triggers closure at step N, or none of them do. No exceptions, no middle ground. And when it does close, something beautiful happens. You get a whole infinite family of polygons, one for every starting point, each one a different shape, all inscribed in the outer conic, all tangent to the inner one. They live together, in perfect synchronized motion. So this is what we want to explain. Why is closure locked to the pair of curves themselves, and not to where you start? That's the mystery. Let's start with the simplest case where we can actually compute the answer. Two circles, outer circle, radius big R, inner circle, radius little r. Their centers sit some distance d apart. We'll assume the inner one fits strictly inside the outer one. The question is, when does the Poncelet triangle close? In 1746, a British mathematician named William Chapple found the answer. He published it in a popular magazine of the time called The Gentleman's Magazine, and here's what he found. d squared equals r squared minus 2rr. That's it, one equation, three quantities. If the radii and the center distance satisfy this equation, every triangle you try closes. If they don't, no triangle closes. Let's see it with actual numbers. Say the outer circle has radius 5 and the inner circle has radius 2. Chapple's formula then says d squared should equal 25 minus 20, which is 5, so d equals the square root of 5, around 2.236. Place the two circles with those exact numbers, and the Poncelet triangle closes. Every single triangle. Exactly. Move the inner circle even slightly closer to the center, d gets smaller, and suddenly no triangle closes. Move it slightly further, d gets bigger. Again, no triangle closes. The condition is a razor's edge. About 50 years later, a mathematician named Nicolas Fous working in St. Petersburg did the same thing for quadrilaterals. The condition for a four-sided Poncelet polygon is messier, but it's still a single equation. He kept going. Pentagons, hexagons, heptagons, octagons. Each one a different algebraic relation among the same three numbers r, and d. Every n has its own equation, but every n has exactly one. So what Poncelet's theorem tells us, in the two-circle case, is this. There's always exactly one condition per n. A single relation that locks down closure, independent of where you start. And the theorem doesn't just cover circles, it covers all pairs of conics. For general conics, the relation is harder to write down, but it exists. Closure is governed by a single equation in the geometry of the two curves and nothing else. This is still magical. A single equation picks out an infinite family of perfectly closing polygons. That's a lot of agreement from a single line of algebra. So the real question becomes, where is this agreement coming from? To see where the all or nothing is coming from, let me strip the problem down to something as simple as possible. Imagine just a single circle, not two, just one, and instead of tangent lines, you have a single fixed step. 60 degrees counterclockwise. Start anywhere on the circle. Take the step, you're 60 degrees further along. Step again, 60 more, and again. After exactly 6 steps, you've gone all the way around, and you're back where you started. Now the important thing. Start from a different point on the circle. You still come home after exactly 6 steps. The step size is fixed. It doesn't care about the starting position. 6 60-degree steps make 360 degrees no matter where you begin. That's obvious. But look at what it has in common with Poncelet. We have a fixed step. Closure at step n means that step applied n times brings you home. Whether it closes doesn't depend on the starting point, because the step size doesn't depend on the starting point. What we want to do then is find a way to see the Poncelet construction as a fixed step operation. We want some closed loop, and we want Poncelet to move us along that loop by a fixed amount every time we take a step. If we can find that, closure becomes obvious. You add the fixed amount to itself n times. If you've gone around the loop a whole number of times, you're home. So the question is, where's the loop? Here's the trick. Instead of tracking just the point P on the outer conic, track a pair of things. The point P together with the tangent line from P to the inner conic. From a general point on the outer conic, there are 2 tangents to the inner one. So for each position, there are 2 pair objects. Point plus tangent. Now, and this is the surprising part. If you take the set of all such pairs and you give them coordinates, the resulting object is not a circle, it's not a line. Topologically, it's a donut. A donut. Mathematicians call this shape a torus, but whatever you call it, it's a closed loop and it's the right object for our problem. And on this donut, the Poncelet construction moves every point by a fixed amount. Every time you take a Poncelet step, point to next point, together with the new tangent, you're moving a fixed distance around the donut. That distance is determined entirely by the 2 conics, by their shapes and their relative positions, not by where you started on the outer curve. And now the theorem is essentially obvious. Closure at step n means n copies of the fixed step make a complete loop around the donut. Whether that's true depends only on the step size, that is, only on the two conics, not on where you started. The step does the work. The starting point just rides along. The loop we just met isn't any old donut. It's what mathematicians call an elliptic curve. The name is genuinely confusing. An elliptic curve is not an ellipse, it's something deeper. It's a particular kind of loop on which you can add and subtract points, the same way you add and subtract numbers. Given any 2 points A and B on an elliptic curve, there's a uniquely defined third point called A plus B. It's built out of drawing lines and finding intersections, but it is a real addition. It's associative, it's commutative, there's a zero element. The elliptic curve is secretly a group. And what the Poncelet construction does on its elliptic curve is really just add the same element over and over. Call that element delta. The walk is 0, delta, 2 delta, 3 delta, 4 delta, just like counting. Closure at step n means n times delta equals 0 in the group. In group theory language, we say the element delta has order n, and the order of a group element is a property of the element, not of where you start adding it from. That's the entire theorem. Closure doesn't depend on the starting point because the group operation doesn't depend on the starting point. This same group law, by the way, is what runs most of modern cryptography. When your browser tells you a connection is secure, there's almost certainly an elliptic curve in the background, doing exactly the same kind of addition. So Poncelet's theorem, which looks like a question about polygons drawn between two curves, is actually a statement about the order of an element in an abelian group. A beautiful kind of disguise. This insight was made precise by Jacobi in 1828, using the theory of elliptic functions, and modernized by Griffiths and Harris in 1977. But if you squint, the idea is already visible in Poncelet's original treatise. The bouncing polygon is secretly walking on a torus, one fixed step at a time. Here's one more way to see the theorem. I think it's the most beautiful one. Forget the tangents for a moment. Imagine you're standing in a room shaped like an ellipse, perfectly smooth walls, no friction. You have a billiard ball and you shoot it. It bounces off a wall. Angle in, angle out, the way billiards always work. Then it bounces off another wall and another, tracing a long, zigzagging path through the room. Here's the remarkable thing. The trajectory of that ball has a hidden structure. If the first segment of the ball's path happens to pass on the outside of both foci of the ellipse, then every subsequent segment is tangent to a specific smaller ellipse, an ellipse sharing the same foci, a confocal ellipse. The ball doesn't know this, the ball just bounces. But the geometry of the ellipse forces every segment of the ball's entire trajectory to kiss the same inner curve. That inner curve is called a caustic. A given initial shot gives you a specific caustic. Every bounce touches it once. And now look at what this is. Two conics. The outer ellipse of the room and the confocal inner ellipse. A chord of the outer, tangent to the inner. Bounce. Another chord of the outer, tangent to the inner. It's Poncelet. Every bounce of the ball is a Poncelet step. Every caustic is the inner conic. Every elliptic billiard is secretly a Poncelet machine. And so Poncelet's theorem translates into a statement about billiards. On an elliptic table, either every trajectory with a given caustic returns to its starting position and direction after exactly n bounces, or none of them do. Take a moment to feel how physical that is. You aim the ball one way, and after 6 bounces it comes back to where it started, moving in the same direction. Wonderful. Now aim again, carefully, so that the new trajectory has the same caustic. The new trajectory looks completely different. Different bounce points, different angles of incidence. It's a visually completely different shot. And after exactly 6 bounces, that one comes home too. The period is a property of the caustic, not of the shot. The ellipse, once it's been built, has already pre-decided, for every possible caustic, exactly how many bounces it takes for a ball with that caustic to return home. There's a twist in the story of how we came to know any of this. Jean-Victor Poncelet was 23 years old in 1812. He was a lieutenant of engineers in Napoleon's Grande Armée, marching into Russia. At the Battle of Krasnoye, in November, he was left on the field for dead. Russian soldiers found him alive the next morning and marched him east, on foot through the snow, for 5 months, to a prison camp at Saratov on the Volga. He stayed there 18 months. No paper, no books, no instruments, just charcoal and the walls of his cell. He worked out what he could remember of Gaspard Monge's lectures on geometry, and then he kept going. By the time he walked out in 1814, he had the outline of a new branch of mathematics in his head. He spent the next 8 years writing it down. He published the result in 1822 in a 1,000-page volume called the Traité des propriétés projectives des figures. The closure theorem is in it. It's a theorem born in a cell, on a wall, from nothing but memory. And the story isn't finished. In the 1920s, an American mathematician named George Birkhoff looked at the elliptic billiard setup and asked a different question. Forget the inner caustic, just ask this. What shapes of billiard tables have the caustic preserving property at all? Ellipses have it. Circles have it, trivially. Is there anything else? Birkhoff conjectured no. The only smooth convex billiard tables that behave this way, he said, are ellipses. 100 years later, we still don't know whether he was right. The best result we have was proved in 2016 by Artur Avila, Jacopo de Simoy, and Vadim Kaloshin. They showed the conjecture holds locally. Any smooth convex table close to an ellipse that has the caustic preserving property really does have to be an ellipse. You can't smoothly deform an ellipse into something different and preserve the property, but globally we don't know. There could be some wildly non-elliptical shape, somewhere out there in the space of all convex shapes that happens to behave this way, for reasons nobody has yet seen. So this is where we land, a theorem written in 1822 about polygons drawn between two curves, a deep reason uncovered in 1828, connecting it to the group law on an elliptic curve, a physical reframing in the 1920s, connecting it to the bounces of a ball in an elliptic room, and a question still open today about whether the ellipse is the only shape that allows the whole beautiful structure to exist at all. Every time someone sets a ball in motion on an elliptic pool table and watches it trace a periodic orbit, they're playing inside a proof Poncelet wrote from memory on a prison wall 200 years ago. That's Poncelet's closure theorem.